A very good morning to all students. In the previous class, we were discussing about electric field. Electric field is one of the space around the charge which can experiences electrostatic force. It is called electric field. Electric field is the vector quantity. Based on that, we were discussing about electric field due to a point charge. In that, we obtained the expression for electric field. How much electric field can charge experience? That force per unit charge. Force experienced per unit charge is called as a electric field. It is denoted by letter E. The final equation we found to be 1 by 4 pi epsilon naught Q divided by R squared and then R cap. Here R cap is unit vector. And after that we were discussing about important aspects of electric field. We will discuss one more time, short and sweet. If the charge Q is positive, then the electric field points away from the source charge. If it is negative, electric field points towards the source charge. And the force, electrostatic force in terms of electric field can be calculated as F vector is equal to Q naught and then E. This is Coulomb's law in terms of electric field. Okay. And the electric field is independent of the test charge Q naught and it depends only on the source charge, which means that until or unless bringing another one test charge Q naught towards the charge Q, we could not able to detect the presence of electric field around the charge Q. Yes. Next one, as the distance increases, the electric field decreases in magnitude because electric field is inversely proportional with the square of the distance between them. The test charge is made sufficiently small so such that it will not modify the electric field of the source charge. For continuous and finite charge distribution, integration techniques must be used. Based on this aspect only, we are going to start the today's class. The topic is electric field due to system of point charges. What's the meaning of it? System of point charges, which means that in that particular system more than two charges, many number of charges are present. What is the value of electric field produced by the only one charge? So that can be calculated in the concept of today's class, electric field due to system of point charges. Suppose a number of point charges are distributed in space. To find the electric field at some point P, due to this collection of point charges, superposition principle is used. Yes, superposition principle technique already we have used in a previous class for calculating the total force acted on one charge due to many number of charges present in a system. This is a superposition principle applied for calculating the total force. According to this superposition principle, total force acting on a given charge is equal to vector sum of forces exerted on it by all other charges. So this is applied for the Coulomb's law. So based on this same concept of superposition principle, we can apply for calculating the total electric field due to system of charges on one charge. By using this concept only, we are going to calculate the electric field value. The electric field at an arbitrary point due to collection of point charges is simply equal to the vector sum of the electric fields created by the individual point charges. This is called as a superposition principle of electric fields. I will repeat the statement of superposition principle in terms of electric field one more time. The electric field at an arbitrary point due to collection of point charges is simply equal to the vector sum of the electric fields created by the individual point charges. This is called superposition of electric fields. Let us consider a collection of point charges Q1, Q2, Q3 are present in this system. We are going to consider the point P here. In this point P, we kept one test charge called as a Q naught. The distance between each charge is mentioned. charge distance between charge to the point is mentioned as R1P. R2P is the distance between Q2 charge to P. R3P is distance between Q3 charge to P. So here that is arrow mark, what is the meaning for it? So at a point P, the electric field can acted due to positive charge, it is acting away from it. So this red color arrow mark represents electric field produced by the first charge from the point P. So it is denoted by letter E1P. So that value can be calculated as E1 vector. So what is the E1 vector will come? 1 by 4 pi epsilon naught Q1 divided by R1 P squared into R1 P cap. So like that we can calculate for the electric field 2. So this is second charge Q2 placed here. The distance between it is taken as R2P. Electric field is mentioned in terms of green color arrow mark. That green color arrow mark represents electric field produced by the Q2 charge from the point P. Why its magnitude is lesser than this previous one? Look at the distance between both. Q1 to P is distance very smaller. Hence it produces a greater electric field. Space between Q2 and P is very larger. So it produces a less electric field. Yeah. And the third one. So third one is mentioned in the violet color arrow mark is electric field due to third charge. So like that we can calculate the total electric field by using the superposition principle. So by adding all the individual values, nth charge also we can able to identify and we can mention it as a En vector. And then by adding all the values, here 1 by 4 pi epsilon naught is constant. We are taking all the constant values outside from each term and remaining Q1 divided by R1P squared and R1P cap plus Q2 divided by R2 squared, R2P cap plus Q3 divided by R3P squared, R3P cap plus till etc. Then Qn divided by Rnp squared into Rnp cap. So this is the total electric field we found with help of the superposition principle. By considering these all values, we are going to calculate the direction of total electric field. For that, in 11th standard we studied about triangular law of vector addition and parallelogram law of vector addition. So this vector is without changing direction drawn from the head of the first vector. So this is E2P is mentioned here, and another one, this is the third vector is taken and then joined with the head of this vector and then we connected here. The closing side is taken as a total electric field. It is mentioned in the blue color. So this is large total electric field value due to system of these three charges from the point P. It is acting in this direction. Okay. Then total electric field in magnitude is written as a 1 by 4 pi epsilon naught. This all terms can be simplified by using the summation term by introducing the ith component of charge Q. So here at summation I is equal to 1 to n. Instead of Q1 and Q2, Q3 commonly we are writing as a Qi. So that I value takes from 1 to n values and divided by Rip the whole squared into Rip cap. So with help of this formula we can write the total electric field due to system of point charges found by superposition principle. Okay, the next topic is electric field due to continuous charge distribution. The electric charge is quantized, calculated or measured in terms of microscopic system only. The expression of electric field E vector is equal to 1 by 4 pi epsilon naught Q divided by R squared, and after finding the superposition principle we have derived the previous one. No? So this expression applicable to only point charges while dealing with the electric field due to charged sphere or a charged wire etc. It is very difficult to look at individual charges in these charged bodies because the type of all objects are made up on a infinite number of uncountable number of electric charges within a body. Therefore, it is assumed that the charge is distributed continuously on the charged bodies and the discrete nature of charge is not considered here. By using that formula, quantization of electric charges Q is equal to Ne formula, we found it. But in this, the electric field due to such a continuous charge distribution is found by applying the method of calculus for calculating the total charges, electric field produced by the total charges within objects. For that we can use the integration method can be applied. Okay. Let us consider this irregular shape of an object. In this object there are a number of charges are located. We are going to consider only the three number of charges considered as a del q1 charge within this place, and del q2 charge, and then del q3 charge. Like this we can apply for n number of charges. Del qn charge also can be applied. Here del q is taken as a point charge element, charge element. Okay, the electric field, how to calculate the electric field? The electric field at a point P due to charged object is approximately given by the sum of the field at a P due to all such charges. At this point only we are going to calculate the total electric field by using the superposition principle. So by applying that concept we can identify that value of electric field approximately equal to, not exact value, approximately equal to 1 by 4 pi epsilon naught summation of I is equal to 1 to n del qi divided by ri p squared ri p cap. Okay, for calculating exact value, how to find out the total electric value exactly? For that we are going to take the integration method only. So to incorporate the continuous distribution of a charge, we can take that all limit value as del q value is taken as up to 0. When this del q approaches 0, this summation can be converted into integration. We studied in a second unit of 11th standard. When this value of del q approaches 0, not exactly 0, approach going to reach value of 0, this summation can be changed into integration. Now this equation becomes E vector equal to the same constant 1 by 4 pi epsilon naught. Instead of this summation we are writing only dq, integration and dq. Here that del q is changed into dq, the same distances, divided by r square and then into r cap. Here r cap is nothing but a unit vector only, and its direction is r cap is a unit vector from dq to point P. It is acting from dq to point P. Even though the electric field for a continuous charge distribution is difficult to evaluate, the force experienced by some test charge q in this electric field is still given by the same formula, F is equal to q into E vector. If the charge q is uniformly distributed along the wire or rod, how to calculate the value of electric field? Because that objects present in the universe are different in their size and shape. For a different, with respect to their shape, the charge distribution is different. So for that, how to calculate the electric field value produced by the charge present in a one wire or rod. So we will start from that first one dimension. So for that, linear charge density is introduced here. Before discussing about it, let us consider a charged wire or rod. It contains the q amount of electric charge present in the distributed fully in this linear charged wire. In that total length of the wire is taken as a capital L. So what is charge density? Linear charge density means amount of charge per unit length. You know that the basic formula for density is mass per volume. Here that charge density means charge per unit length. So linear charged wire, it is taken as a linear charge density lambda. It is denoted by letter of lambda. It's equal to Q by L. In this linear charged wire, we are going to consider the very smaller portion, infinite similarly small of portion assumed that length is taken as a dl value. Let us consider the point P away from the rod. From this point P, what is the electric field due to this charged wire? So distance between the point P and then wire is taken as a R value. Here that unit vector is taken as a R cap. So for calculating the total charge present within this dl portion, we can take this as a lambda is equal to q by L means, so that same charge density only located in that area, so that lambda is equal to amount of charge is dq divided by length is taken as a dl value. So that value of lambda is equal to dq divided by dl. Based on this we can calculate dq. So dq is equal to, take this dl to left side of the equation and convert it into multiplication term. So lambda into dl. So this is the amount of charge present in this smaller portion of the charged wire. So what is the unit for linear charge density? We know that lambda equal to q by L. Here q is electric charge, L is length. So charge is measured by coulomb, length is measured by meter. So this is SI unit of linear charge density. Based on this we can calculate the electric field at a point P due to this linear charge wire or rod. So electric field, basic equation, electric field E vector is equal to 1 by 4 pi epsilon naught integration. Why we are using integration? Because of continuous charge distribution in this area or this surface. So we are writing integration. So dq divided by r squared into r cap. So dq is very small amount of charge present in the smaller portion dl. So substituting the value of dq in this formula, we can write it again, 1 by 4 pi epsilon naught integration of lambda into dl divided by r square into r cap. By taking the value of lambda as constant in this wire now, so we are taking outside. So lambda divided by 4 pi epsilon naught integration of dl divided by r squared into r cap. Here unit vector r cap is acting from that smaller portion area to the point, considered point P. So this is expression for calculating electric field due to linear charged wire or rod. And the next one is if the charge is uniformly distributed on a surface area of A. Let us consider this is one surface area. The area value is taken as a capital A, and then Q amount of electric charge is present in this surface fully. For calculating the electric field value, we are going to introduce the concept of surface charge density. Here, what is the meaning of density? Charge density mean it is denoted by letter sigma here. Surface charge density sigma is equal to amount of electric charge per unit area, because this area can be calculated. Here that area is taken as a, it may be calculated as length into breadth. So surface charge density is defined as amount of charge present in a unit surface area is called as a surface charge density, and we can calculate the SI unit for it. Charge is measured by coulomb, area is measured by meter power minus 2. If we take into numerator, we can write as meter power minus 2. Okay. So in this we are going to consider the very smaller surface area. That smaller surface area is considered to be dA value. So what is the charge present in this smaller surface area? So for that we can use this concept. So d sigma is equal to amount of charge present in a dA area is dq by dA means in this dA is taken to left side, we can calculate the value of dq. By substituting the value of dq in the common formula, we are calculating this value electric field. So electric field E vector is equal to 1 by 4 pi epsilon naught integration of sigma dA divided by r squared into r cap. Taking the constant of proportional outside, sigma divided by 4 pi epsilon naught sigma dA divided by r square r cap. Here constant of proportional, which means the sigma means amount of charge density. It is always constant only. That's why we have taken outside of the integration symbol. So this is for a calculation of electric field due to continuous charge distribution in a surface area. So next one is volume charge density. Suppose charges are continuously distributed in a volume. How to calculate the electric field value? For that only we are taking this as volume charge density. It is denoted by letter rho, equal to amount of charge present in object divided by total volume of the object. So for that, let us consider the one irregular shaped object. In that irregular shaped object, amount of charge q is presented, and then volume of the charge, volume of this irregular shaped body is taken as a v. Let us consider the point out of the shaped irregular shaped object p located with the distance of r. The unit vector is acting from this r cap, which means that in this place only we are going to consider the very smaller portion of volume. So that smaller portion volume consisting of a dq amount of charge with a smaller volume of dv. So we can calculate the value of volume charge density. Amount of charge per unit volume. The SI unit is taken as a coulomb meter power minus 3. For calculating the volume charge density of the smaller portion, we can use this one. So rho equal to dq divided by dv value. By total value of electric field 1 by 4 pi epsilon naught integration of dq divided by r square into r cap. Substitute the value of dq here and then calculate the electric field. So finally we are getting electric field E vector is equal to electric field E vector is equal to rho divided by 4 pi epsilon naught integration of dv divided by r square into r cap. By using this all concept, we can calculate the electric field due to continuous charge distribution. This picture shows that continuous charge distribution of linear charge at object, surface area and volume objects. First one is linear charge distribution, we can use this one. Surface charge distribution, we can use this formula. Volume charge distribution, we can take this one. Thank you. And the next one important topic is electric field lines. We know that electric fields are vector quantity. It has a magnitude and a direction. Magnitude can be calculated by using the formulas we seen in the last topic. E vector equal to 1 by 4 pi epsilon naught q divided by r squared. The direction can be calculated by drawing on vector line. So here that electric field vectors are visualized by the concept of electric field lines. Electric field vectors are visualized by the concept of electric field lines. They form a set of continuous lines which are the visual representation of the electric field in some region of space. For drawing the type of electric field lines, we have to follow some rules. We will discuss that. So I repeat one more time, what is the electric field lines mean? It is on imaginary straight or curved lines drawn in an electric field. In that, it is act as a one path for the electric charge. In that electric charge tends to move in an electric field from one point to other point by experiencing the electrostatic force. The following rules are followed while drawing the electric field lines for electric charges. So let us consider the two charges, plus q charge and minus q charge, is separated by a small distance. We know that these two, unlike charges, are always attractive. It experiences attractive electrostatic force. So some force due to action of some force, any one of the charge might be attracted towards each. Any one charge can move from one place to other place towards other charge. For that only that at what path it is moving. So for that we can draw the electric field lines. The type of electric field lines always start from positive charge and end at negative charge. So this type of all red color lines, it is all represents that electric field lines only. So electric field lines always start from positive charge and end at negative charge or at infinity. It end at infinity. Second one, for a positive point charge, the electric field lines point radially outward. So here it is a positive charge, isolated positive charge. It is always emits the number of electric field lines away from the charge. Look at here, for a positive point charge, field lines are all directed radially outward direction only. Note that for an isolated positive point charge, the electric field lines start from the charge and ends only at infinity. And another one is for a negative point charge, electric field lines point radially inward direction. Look at this is a negative charge, the minus q charge is kept here. The number of electric field lines are acting infinity from infinity to point charge. For an isolated negative point charge, the electric field lines start at infinity and end at the negative charge. It is acting radially inward direction. Due to positive charge, electric field lines acting radially outward. Due to negative charge, it is acting radially inward. And for finding the direction of electric field lines at a point P, we have to draw one tangent line. So this is next rule. In this electric field lines, if we consider any one point P, in that point we can find out the direction of electric field lines by drawing on tangent line. So from the point P we have drawn on tangent line. This tangent line represents that direction of electric field. The tangent line denotes that direction of electric field. Here also we can calculate. If you draw on tangent line from this point, it is acting towards this direction. We can find out the direction of electric field. So electric field vector at a point in space is tangential to the electric field line at that point P. And the next point is the electric field lines are denser in a region where the electric field has large magnitude and less dense in a region where the electric field is of smaller magnitude. So meaning for this point is the magnitude of electric field is directly proportional to number of electric field lines present in that unit area. So in this picture, one isolated positive charge is kept. It is producing a number of electric field lines away from acting radial outward direction. We are going to consider the two surface area A and other area is taken as a B. The surface area A is considered very closer to the positive Q charge, and another one B is far away from the charge. Look at here, in this surface area A, there are more number of electric lines of force are crossing. Here only less number of electric lines of force only crossing, which means that wherever the electric field lines, counting of electric field lines is maximum, in this place electric field is maximum. If it is electric field lines is very less number, electric field will be minimum. In other words, wherever the electric field lines are close with each other, electric field is maximum. Wherever electric field lines are away from each other, far away from each other, so that time electric field strength is very, very minimum. So hence we can conclude for this property is electric magnitude value of electric field is directly proportional to number of electric lines of forces present in the given unit area. And another one important point is no two electric field lines intersect each other. Electric field lines are never intersect each other. Why? What is the reason for that? Why it is not intersecting means, look at this picture. In this there are two electric field lines is drawn cross direction. We are going to consider the point P, that where the point of intersection we kept on point P. In that on charge is placed. If you place one charge here, electric field lines mean it is a path. It is behave like a path for moving electric charges. No, so if after placing one charge in the point of P, due to action of two electric field lines, this type of charge has to move in this direction and in this direction. At the same time, it is not possible. It will move only one direction only. No, so for that is the reason for this one. No two lines intersect each other. I will repeat once. No two electric field lines intersect each other. If two lines cross at a point, then there will be two different electric field vectors at the same point as shown in figure. As a consequence, if some charge is placed in the intersection point, then it has to move in two different directions at the same time, which is physically impossible. Hence, electric field lines do not intersect each other. And the last property is the number of electric field lines that emanate from positive charge or end at negative charge is directly proportional to the magnitude of the charge. So how many number of electric field lines are emanating, producing from the one charge now? That number of electric field lines is mainly depends upon the magnitude of the electric charges. For understanding this concept, let us consider plus Q charge. So this plus Q charge is emitting 1, 2, 3, 4, 5, 6, 7, 8 number of electric field lines. This number of electric field lines is depends upon the magnitude of the charge. Comparing to this charge, another second charge. First magnitude of charge is plus Q, second magnitude of the charge is minus 2Q. Minus Q charge means electric field lines will be acting inward direction. Minus 2Q compared with the previous one, the magnitude value is double of the first one. Now count the number of electric lines of forces from this 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. So here 16 electric field lines are produced due to 2Q charge, minus 2Q charge. Here 1Q charge only, so hence it produces the 8 number of electric field lines. So depends upon the value of magnitude only electric field lines are emitting. So first Q charge, only 1Q charge now, it producing 8 lines. Compared with this magnitude, second one minus 2Q mean 16, and third one it may be changes. How much value? If it is 3Q charge na 24 lines is emitted. So not only this one, Q means only 8 lines. It is one example for comparing the value of this. Okay, we came to end of the class. Just we recapitulate once about the concept of properties of electric field lines. They start from positive charge and end at negative charge or at infinity. For a positive point charge, the electric field lines point radially outward. For a negative point charge, the electric field lines point radially inward. The electric field vector at a point in space is tangential to the electric field lines at the point. The electric field lines are denser in a region where the electric field has large magnitude and less dense in a region where the electric field is of smaller magnitude. No two lines intersect each other. The number of electric field lines that emanate from positive charge or end at negative charge is directly proportional to the magnitude of the charges. Okay, so these are some important properties of electric field lines of forces. Okay, as usual, I will send the study material for this topic after finishing the classes. Please prepare thoroughly and write the test on appointed time. Don't think that we can write the test at the time before the day of school reopening. Don't want like that. Get ready for writing test coming Friday, and I will give the questions with the quiz. Write the test with the parents' permission, get parent signature, and bring the test paper on the day of school reopening. Thank you students.